This is for assignment 5. This is a video for assignment 5. I'm going to go back over a bunch of stuff from assignment 4, but I'm going to go through it very quickly. Correlation. Correlation is just a relationship between your two variables. That's what we're trying to figure out here and read here is how well are these two variables correlated. Remember, your x is your independent variable and your y is your dependent variable. We're trying to figure out how those two are related to each other, or if they are related to each other. Scatter plot, hopefully you can draw a scatter plot by now. Scatter plot, once we have the scatter plot and we come up with a line, a best fit or a regression line, then we can make predictions off of either the equation or the line itself. Remember that domain is all your x values, range is all your y values. Be able to tell the correlation, whether you have a negative correlation, a positive correlation, or no correlation. Remember, a negative correlation is going, as the x's get bigger, the y's get smaller. Positive correlation, as the x's get bigger, the y's get bigger. And then no correlation is just when it's all scattered everywhere. And again, we didn't do a whole lot with nonlinear. We're not going to do a whole lot with that right at the moment. If you wanted to put the scatter plot in the calculator, you could do this. I'm going to skip over this. Regression line or line of best fit. You can draw in a line of best fit, but you only want to draw it after you make sure that there is some kind of correlation between your x's and your y's. If there's no correlation, if it just, it's just scattered everywhere, and there's points all over the place, something like this, then one person could draw a line of fit in like this, or a line of best fit in, another person could draw one in like that, so there really is no correlation. So we have to make sure that there is some kind of correlation between the two first. The residuals, we talked about this on assignment 4. The residuals, we don't want to have to do this every time, but the residuals are how far each point is off of what we would predict if we were at that point on the data, and we want the minimum to get that line of best fit or that regression line. We want the minimum of the sum of all of those squared. Now, I'm not going to talk about that a whole lot because we're not going to do a whole lot with it. Remember, your equation of your regression line is y hat equals mx plus b. M is the slope, b is the y-intercept. Instead of m here, our calculators use a, and they use b for that one. Once we know this equation here for a regression line or a line of best fit, then we can make predictions by plugging into that equation. And we use these formulas. I showed you last time to use these formulas. You could use the formulas and do it out longhand and figure out, and we use the chart, and we're going to use that chart again, but we're going to use it for to find R instead of this. But most of the time we're just going to use our calculator. One thing I will say is remember that your regression line is always going to go through that point where it's the mean of all the x's and the mean of all the y's. This is that chart that we used to find M and B. Last time we didn't use this column to find R this time. We're going to use that column, so we're going to use all these columns. But this was to find M and B, which then you used your calculator to find, and that's what we're going to skip to next. I did this out and did this one for you longhand last time. Remember, be able to explain this stuff, being able to explain this, what we're doing is probably one of the most important things. If you can't explain something, then it doesn't mean anything. With this, If our slope is 196.152, remember there's always a 1 underneath there. This is telling you that for every 1 that the x's move to the right, the y's go up that amount. If it was a negative, then they'd go down. So our explanation here, for every $1 trillion of GDP, the CO2 emissions goes up 196 metric tons. Then the explanation of the y-intercept, if we're looking at this, that's where the line crosses the y-axis. So that's where x is 0. So we're saying if somebody has $0 trillion of GDP, then their CO2 emissions would be about 102 million metric tons. So be able to explain those. This one we used the calculator on. This is the steps they used in assignment 4 to punch this into your calculator to come up with your A and B when you are looking at the screen. And it says something like linear regression, y equals ax plus b. And then underneath it, it tells you what A is, it tells you what B is. And if you did what you were supposed to do, it should also tell you what R squared is and what R is. So if you didn't do that, I sent a video out over spring break to tell you to do something to your calculator and send it back to me, and that will count as an assignment so that it shows up R squared and R. If it's not showing up, then you need it to show up. So go back and look for that video and make sure you send in a picture of your calculator so that I can write you down as having that assignment completed. A, remember, is your slope. B is your y-intercept. R squared is called the coefficient of determination. We're going to talk about it later. And R, we talked a little about last time, we're going to talk more about this time, is your correlation coefficient. This is what the screen looks like. It should look something like that. Again, if you haven't fixed your calculator, you have to go in there and do that I showed you on the video. And then if we wanted to write our equation would look something like that. Y hat equals 12.481 plus 33.68, and they didn't round those very far. I wouldn't have any problem with you rounding that to 12.5 and 33.7. Remember, interpolation is when you're making a prediction inside the given data. So if your domain, if your x's run from the lowest maybe is 5 and the highest is 17, so we're going 5 to 17, then any numbers that we pick that fall in there, then it's interpolation. If we pick numbers outside of there, like if we picked 19, then we're doing extrapolation when we're making a prediction. And you only want to make these predictions if your line of best fit actually fits the data. If the data is just random and there is no line of best fit, then it's not going to work out very well. And still, a lot of the times it won't work out real well for extrapolation. We did this last time. This is just, they gave us the equation and we're plugging in there to make predictions. Correlation of coefficient, this is where this time starts. The correlation of coefficient, that's your R. That's what we're going to deal with, is a measure of the strength of the direction, strength and direction of a linear relationship. So when it's talking about strength and direction, strength is how well are they correlated, and the direction is just telling you whether it's got a positive correlation or whether it has a negative correlation. R represents a sample, so R is the correlation coefficient for the sample, and then this symbol is rho, and that's for a population. So R is for a sample, rho is for population. Just like X bar and mu, X bar was for a sample, mu was for the population, same idea here. This is the formula to find R. Again, another crazy formula, and we're going to learn how to use our calculators to find that, but I'm going to show you how to do it out longhand. Correlation coefficient is always going to fall between, so R is always going to fall somewhere between -1 and 1. The closer you are to -1 or 1, the better correlation is, the better that the variables are related, so the better that the X and Y are related. The closer you are down here to 0 on either side, then that means the variables, the X and the Y, aren't related very well. Means what X is doesn't really affect what Y is going to come out to be. If we're right here on -1, then that means we have a perfect negative correlation, and what that tells you is that if you made a prediction of what Y is going to be given some X, every single time it's going to come out exactly that. That doesn't happen very often. Most of the time will be somewhere in this range, not exactly out here on -1. Then if you're close to 0, there's no linear correlation. And if we're close to 1, then it's, if it's exactly 1, it's a positive or a perfect positive correlation. Again, most of the time that won't happen. Most of the time our R will come out to be, maybe something like 9 or 0.972 or something, which is somewhere about in here. And that means that there's a really good correlation between the two sets of data, between your X's and Y's. If your R comes out to be something like 0.003, down in here somewhere, very, very bad correlation between them. So that what the X is doesn't really affect what the Y is going to come out to be. Same idea on the other side of the line. If your R is -0.005, something like that, not a very good correlation. That means the variables aren't related very well. And if it's way out here somewhere, then it's got a good correlation and the variables are related pretty well. So the closer you get to 0, the worse the correlation between the X and the Y. The farther you get out away from 0, whether it's going to the positive or to the negative, the better the two variables, the X and Y, are related. So this is just an example. Strong negative would be something like -0.91. That's a strong negative correlation. Strong positive correlation, 0.88. A weak positive correlation, you can see these points, how they're all scattered out here, all over the place. 0.42, that's a pretty weak correlation. And then when you get real close to 0, like your R is 0.07, then there's really no correlation. Different books teach different things as far as how you decide whether it's a strong correlation and what the range is for strong correlation or weak correlation. We're not going to talk a whole lot about that. Went too far. This is how you calculate a correlation coefficient. This is how you calculate R. First thing you do is you get the sum of all the x's, and this uses the chart. Get the sum of all the y's. You take each x times each y, and you add all those up. Square each x and add all those up. Square each y, add all those up. And then use that formula to figure out what r is. And I'm skipping over this sort of quickly because I got it on this next slide sort of shortened up a little bit here. So we add up all the x's, add up all the y's, x times y, add up all those, x squared, add up all those, y squared, add up all those, and then we plug into this formula. I'm going to show you an example of finding r, doing it out longhand, and then we'll use your calculator to calculate it most of the time. This is the box again. Again, last time we didn't use this column, but this time to find r we're going to. For your calculator, to use it, or to find r on your calculator, you're going to do these steps. Give you a second to make sure you got that down. You're doing those steps. It's the exact same steps as finding the a and the b, the slope and the y-intercept for your line of regression. This only works again on your calculator if you've done that other video that I sent out, and so that it shows r squared and r. So the next thing we're going to do is we're going to find r and stuff. I'm going to show you how to do that, but we're also going to, at the same time, we're going to use a table that's in the back of the book. And also I sent one to you, or put one on Moodle, and there's one on this PowerPoint that lets us know about the population correlation coefficient, the rho, whether it is significant or not. So in other words, whether the x's and the y's in our sample would actually translate to the whole population, and whether the correlation would be significant, or whether the correlation actually matters. So once your sample correlation coefficient r, once you find it, we can decide whether there's enough evidence to decide whether the population correlation coefficient rho is significant. So, and that's going to be at a specific level of significance. And if you remember our level of significance, that's our alpha. So for this, we're going to use alpha at 0.01 and alpha at 0.05. Those are the two that the chart gives us. Most of the ones that we dealt with was either 1%, 5%, or 10%. Well, this one doesn't use 10% as one of them. So we're deciding whether there is an actual significant correlation between our x's and our y's. It uses appendix number 11 that's in the back of the book. And all it does, or all we're going to do, is we're going to find r, and then we're going to take the absolute value of r. Remember, absolute value just means if r is positive, then it stays positive. If r is negative, then we change it to a positive. So the absolute value, how far that number is from 0 on a number line. And then we're going to decide if there's enough evidence to decide that the correlation coefficient rho is significant for the whole population. All right, so this is just a little piece of the chart, and this is how we're going to use the chart. We know how many pieces of data we have. We have 5, and this time they're saying use a level of significance of 0.01. So we just go here to where it's 5, and we want to go over to the column where it's 0.01, and that number right there, that's our critical value. And all we're going to do with that is we're going to compare it to our R. Alright, so we just want the absolute value of R, and we're saying that if it's greater than, if that absolute value is greater than that critical value, then there is significant evidence, or enough evidence, to say that there's a significant correlation between the X and the Y's in our data. So to do this, these are the steps. Not anything real difficult. Number one, figure out what your N is, how many pieces of sample information you have. Number two, identify your alpha, identify your level of significance. Number three, you're going to figure out your critical value using your chart. So you're going to find the critical value by using the chart. And then number four, you're going to find the absolute value of R and decide whether it's greater than the critical value that you just found off the chart. If it is greater than, then the correlation, the relationship between the X and the Y is significant. If it's not greater than, then there's not enough evidence to support that the correlation is significant. And that's how we interpret it. We just decide, is the correlation significant or is it not significant? So I have a couple examples here I'm going to do real quick, just to show you some of this using the table, and then we're going to talk a little bit about R squared. We're going to find for this, we're actually, and on your home, on the worksheet, you're going to write the equations, the linear equations for the line of regression and so on and so on. So you're going to do a bunch of stuff that also goes back to the last couple of assignments. This says write the equation for the regression line. Well, we're going to do that, but we're also going to do some other stuff. So I have all this data here. I'm going to find R by using this data and doing it out longhand. And I did this. So I got this chart here, and I already went through, this is my whole chart, and I went through and I found the sum of all the X's, the sum of all the Y's. I took X times Y for each one of these, multiplied here, and I got this answer. Then I added all those up. Then I took all the X's and squared them and got all these answers and added them all up and got that. Then I took all the Y's and squared them and got each one of these big answers here, added them all up, and I got that answer down there. And we're just going to use that to plug into the formula for R. This is the formula for R, and I just copied all these down so I could have it here. And N, I have to remember what N was. I believe it was 10. Let's go back and just make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, N. So there was 10 pieces of data. The number in the sample was 10. So I'm going to write 10 up there so I don't forget it. And all we're going to do is take all these numbers and plug into all this. So on top, usually I do the top first. On top we got 10 times the sum of all the X's times Y's, that's that, 15,573.71 minus all the sum of all the X's, which is 23.1, times the sum of all the y's, which is 5,554. So that's all on top. I can probably plug all that into my calculator and just do it right now, and that's what I'd want to do. I don't want to try to do this whole big formula all at one time, otherwise I'll get lost. So if I plug all that into the calculator, I got 10 times 15,573.71 minus 23.1 times 5,554, and I get, so on top I end up with 28. I think I did something wrong here. Let me make sure. End up with 284,034.5. Just wanted to make sure I didn't do something wrong. That's on top. Now on bottom, I can't do all this at one time. You might be able to on your calculator. Just make sure you know how it is with the calculators, and you start putting a parenthesis in the wrong spot or something and it messes up. So I'm going to do just this part first. We'll write down that answer, then I'll do this part, or actually then I'll take this times and we'll plug this in. But first I'm going to do just this part. So n is 10. This is the square root of all this. 10 times the sum of all the x's squared, which is, or all the x squared is 67.35, minus the sum of all the x's and then square it. So we got to take that 23.1 and we're going to square that. Well, I can plug all that right into my calculator, and I get, let's see, if I hit second, square root 10 times 67.35 minus 23.1 squared, close the parenthesis, and I end up with 11.83. Now I got that number in my calculator, and all I'm going to do here, because I know I'm multiplying it times this thing, so I'm just going to hit times, and then I'm going to plug in all of the second part. So times second square root 10 times the sum of all the y squareds, which is 3,775,842.76 minus the sum of all the y's, which is right here, squared, so 5,554 squared, and then hit equals, and I end up with, I think I did something wrong on the top, 31,094.23. I'm going to go back and redo the top here because I think I messed up, probably hit something wrong. 10 times 15,573.71. This is why when you guys are setting in here, I have you work it out on your calculator too, so that if I hit the wrong button, we can figure it out. Yeah. Up here, this is actually 27,439.7. Not sure what I hit wrong, but hit some button wrong. And then I just divide those two. And that's going to give us what our R is. So if I take that number divided by the 31,094.23, I end up with 0.8825. So that's our R. Once we find R, I'm going to write it down on my paper here real quick, and then I'm going to erase some of this so I got more room. once we find R, we want to take the absolute value of R. Well, the absolute value of 0.8825 is just 0.8825. And all we're going to look at is we're going to decide, is that greater than our critical value? Or our critical value, we're going to use our chart, and we're going to use n equals 10 and our level of significance 0.05. I'm going to switch to the next slide here. I have this here, and this is the chart, and we're just going to look at where n is 10, which is right here, and we're going to go out to 0.05, which is this column. So we're right here at this number, which is 0.632. If I go back now, our critical value then is 0.632, and we're going to compare those two and decide if R is bigger than our critical value, and this time it is bigger. So yes, it is bigger, and that means, what that tells us is that there is correlation. There is significant correlation between the X and the Y. Now, if I go back and look at this problem, I can maybe a little better decipher that and give a little better explanation of it. So here, this is where we were dealing with, I can't even remember what we were dealing with, the GDP and the CO2 emissions. So what we're saying is that there is significant evidence, or I'm sorry, there's enough evidence to say that there is a significant correlation between a country's gross domestic product and how much CO2 emissions they put out in a year. All right, on this next one, I'm going to show you this one, but this time we're not going to go through all that. We're going to use the calculator. On the calculator, what you're going to do, you're going to put in all your X's in a list, and you're going to put in all of your Y's in a list. And I've already done that on my calculator. I put in all these in list 1, all the X's in list 1, all the Y's in list 2. You can use whichever list. You just have to remember which one's which one's your X and which one's your Y. They say use alpha 0.05. So if we do all of this, and I punch all that into my calculator, what you're going to punch in, you got all of it in your list. So I have all punched into my list on my or in the two lists on my calculator. I'm going to hit stat, calculate, and then I go down to, you're just following those steps. So stat, calculate, then you scroll down to number 4, which is the linear regression. Hit enter. And then you're going to put in list 1. You got to hit second, number 1. That's where I put it. So list 1. Then you're going to hit a comma, which is right above the 7. And then you're going to hit second, list 2, or whichever list that you put it in. And then you're going to hit enter. And when you get finished, your screen should show you A, B, R squared, and R. It shows you all 4 of those things. Remember, the A and the B are to write the equation of the line of regression, or the regression line. And then the R squared and the R is your correlation coefficient, and the R squared is your coefficient of determination, which we're going to talk about here in a minute. So if I'm looking at my calculator tells me the A is about 12.5. So if I want to write the equation of this line of best fit, I'm going to write y hat equals 12.5x plus our B is about 33.7. That's our equation of our regression line. So if we're looking at this, our regression line, that's our equation for that line that we're drawing on that graph. Then it tells me that R squared, which again we haven't dealt with yet, is 0.958, and R is 0.979. Now what we want to do to see if there is significant correlation is we want to compare the absolute value of that R, which is 0.979. The absolute value of that's just going to be 0.979. And we want to see if it's greater than our critical value. We're going to get our critical value from the chart. We're using these two things to get our critical value. We go down to where we're at 25 is our N, and our alpha, our level of significance this time, is this column. So we match those two up, and it comes out to be that right there, which is 0.396. You'll notice that the R is a lot bigger than that. So that's telling us that there is significant correlation between our X's and Y's. So what that's saying is that we could, if we have an X, we could make a pretty good prediction on what Y is going to be. I'm going to erase all this so that I can do this. And this is a good interpretation right here. There's enough evidence at a 5% level of significance to conclude that there is a significant linear correlation between the duration of Old Faithful's eruptions and the time between them. And that's what those columns were. So we're saying that on those columns, if we go all the way back here, we're saying these are the duration of how long Old Faithful erupts for, and this column is how long till the next eruption. And if we are given a number for X, we can make a pretty good prediction, pretty close, on how long it's going to be. If we sit there and we time how long an eruption of Old Faithful is for, we can make a pretty good prediction using our line of best fit on how long it's going to be until the next eruption. So our equation that we had here was y equals 12.5x plus 33.7, something like that. If we set and we time the eruption, and let's say it comes out to be 2.5 minutes. Well, if we stick in 2.5 minutes right there for X, we can do the math on this and figure out how long it's probably going to be until the next eruption, and be pretty close. All right, for R squared, the coefficient of determination. And some of this won't make a whole lot of sense, but I'll try to explain it after I go through some of it. R squared is the coefficient of determination. It is interpreted as the proportion of the variance in the dependent variable that is predictable from the independent variable. What they're saying there is if we have our graph, and let's say this is our line of regression, there R squared is telling why this point isn't exactly on that line. So the variance or the variation, why the y didn't fall exactly on the line like we thought it was going to. So it's the proportion of the variance of the dependent variable, your y's, that is predictable in the independent. So it's how we're coming up with an idea of why are we not falling exactly on the line. The coefficient of determination is the square of the correlation, so it's just, all that's saying is it's taking R and then you just square it. So whatever R comes out to be, you square that, and that's going to give you your R squared. And R squared that's 0 means that the dependent variable cannot be predicted off of the independent variable. And I should go back to this. The R squared, if we're on the number line, the R squared is always going to be from 0 to 1. No negatives. If we're close to 0, if we're down here somewhere with our R squared, then that means we can't make a good prediction off of our line, our regression line. If R squared is 1, so if R squared is right here, it comes out R squared equals 1, that means R had to equal 1. Then every time we stick in it X and get out our Y, we're going to be exactly correct. There's going to be no error. Everything's going to be exact. And that doesn't happen. All right? There's always going to be some error here and there. So you're probably never ever going to get something where R squared is exactly 1, or most of the time you won't. When R squared is between 0 and 1, that's what's going to happen most of the time, is when it's between 0 and 1. R squared is telling you that whatever the number is, so if R squared comes out to be 0.1, then that means that 10% of the variation in the Y is predictable, or we can explain 10% of that variation. Well, that's not very good. If you can only explain 10% of the variation, then that means if we subtract from 100%, that means that 90% of the variation is unexplained. So when we're down here close to 0 for our R squared anywhere, that's not very good. We can't make very good predictions off of it. When we get up into here, so if we said R squared was 0.90, then that means 90% of why these points don't fall exactly on that line can be explained. And only 10% can't be explained. Again, just to go back over some of this, I know some of this is sort of difficult. R squared is always going to go from 0 to 1. Close to 0 means that you can't really use it to predict using your line of best fit or your line of regression. Closer to 1, that means it's a good prediction of your line of best fit. R squared shows the strength of the linear association between your X and Y. So the closer it gets to 1, the stronger the association between X and Y is. Measures how well the regression line actually represents the data. So, if you have something that's like this, a bunch of points just everywhere, and you're drawing your regression line, well, it's not going to fit the data very well. And this is going to, so your R squared is probably going to be somewhere down closer to 0. And it shows you that, hey, that line doesn't really represent the data very well. And just an example here, if R is 0.922, and we grab our calculator and we figure out what R squared is just by squaring it. So we take 0.922 and we square it. We come up with 0.850. What that's telling us is that 85% sorry, dropped my calculator. 85% of the variation, of the reason the Y varies from the line of best fit, or from the line of regression, is explainable, or can be explained. And if 85% can be explained, then that means that only 15% cannot be explained. So that's what R is. It's telling you a percentage of the variation, or of the variance, that can be explained. All right, hopefully that helps some. Sorry this video was longer than I wanted it to be. The assignment 5, if you have questions, feel free to email me or text me, whatever. Also, here in a few days, I'll probably put up a key for the worksheet, for the assignment 5 worksheet, so that you can sort of check your answers. Make sure that when you're done with assignment 5, you send me a picture of it. Also, I don't have the quiz up yet, but it will be up here soon, that goes along with assignment 5, so be looking for that. It'll just be a Moodle quiz, and you'll do it right there on Moodle. There may be a worksheet that I send along with it. You'll just have to put your answers in. I'll explain that in the directions.